So looking at this, I'm still going to check really quick if it might possibly be a u substitution by thinking about what's the derivative of the bottom, but the derivative of the bottom is going to be a 4x cubed something, and we don't have an x cubed in here. So the next thing I'm going to check is, are my powers the same on the top and the bottom, or where is my biggest power of x? That biggest power of x is in the denominator, so I don't have to worry about long division. Next, I'm going to say, hey, does the bottom factor? And it does, because this has quadratic form. I can take that x over x to the 4th plus 6x squared plus 8 and look at the bottom as almost the same thing we just had, but instead, this time it's going to be x squared plus 4 times x squared plus 2. I know this one's messy, but I figured we'll practice a messy one here. So thinking about breaking this apart for partial fractions, both of these are irreducible quadratics, meaning there isn't a way to factor either of these denominators any more than they currently are. So that x squared plus 4 is going to require a linear term on top. And another linear term on top. So I'll be honest, I got that far, and then I went, that's kind of crazy to think about having to solve for 4 constants in a problem. I wonder if there's a more clever way to do this. So taking another look at where we started, one option we would have is to actually think about from this point doing a u substitution. So I've gotten a lot of questions by email of how do you know to do a u substitution? Well, the truth is that sometimes there is another way to work through the problem, but when that other way looks really messy, I'm going to ask myself just sort of one more time, does the derivative of one part equal the other part? So if I come back here and I instead think about letting u equal x squared, well, that would make du 2x dx. And I have that x dx in the original problem here. So that x dx, I'm going to be able to replace with 1/2 du is equal to x dx. If I make that substitution to the integral right away, then this turns into 1/2 of 1 over u plus 4 times u plus 2 du. I'm still going to need to do partial fractions on this, but now I have it written in a way that I have 2 linear terms, which means when we go to do the partial fractions, we'll only need constants on top. We won't need to have these linear terms on top. So now, kind of starting from here, I'll have 1 over u plus 4 times u plus 2 is equal to a over u plus 4 plus b over u plus 2. And when I multiply everything by that common denominator, I'm left with 1 is equal to a times u plus 2 plus b times u plus 4. Plugging in my nice numbers this time would be u equals -2, and I'd have 1 this piece would go to 0. When I plug in -2, -2 plus 4 gives me a +2. So I'd have 1 is equal to 2b, or b is equal to 1/2. When I plug in u equals -4, I'll have 1. When I plug in -4 plus 2, I get -2. So, and back here, when I plug in -4, I'll have 0. So I'm going to end up with 1 plus a times -2, or a is equal to -1/2. Bringing that back down, I can now break apart this integral. And just to save myself the space, so I know that 1/2 is going to apply to both pieces. And above my u plus 4, I need my a value of -1/2. And above my u plus 2 term, that needs to be my b value of +1/2. And I'm going to finish off the integral, but skip a step. Multiplying the 1/2 by -1/2, I'll have -1/4. When I integrate this, I'll end up with natural log absolute value of u plus 4. But I'm going to go ahead and plug that u back in and call that x squared plus 4. Here, when I distribute that 1/2 in, I'll have 1/2 times 1/2 to get 1/4. This remaining integral would be natural log absolute value of u plus 2. And again, I'm going to go ahead and plug that x squared in directly and have x squared plus 2 plus c.